Hi, this is just a quick introduction to the Avnet Z-Board and Analog Devices AD FMCOMMS3 with the IIO Oscilloscope. My name is Robin Getz and I'm an engineer with Analog Devices. The FMCOMMS2 board is an FPGA mezzanine card which is designed to plug into many different carriers. The chips on it include the AD9361, some power parts, and a small voltage monitoring part for doing housekeeping. The AD9361 is a high-performance, highly integrated RF Agile Transceiver. Its programmability and wideband capability make it an ideal solution for a broad range of transceiver applications. It's a full 2-receive, 2-transmit solution, which includes things on the receive path such as LNA, mixer, analog filters, ADCs, digital half-band decimation filters, and a programmable FIR. On the transmit side, it still has the programmable FIR, digital interpolation filters, DACs, analog filters, mixer, digital attenuation, and in the output mux. We've tried to make things a little bit more convenient for ourselves by bolting everything together in a little Pelican case, but things are exactly the same if you had your own setup. This has the Z-board, the FMCOMMS3, keyboard, power supplies, everything all in one. All we do is open it up from the bottom, flick a little switch, grab all the power supplies, keyboards, cables out, put them on the table, have a look, make sure we plug things into the right adapters for what we need, grab the cables, plug the HDMI cable into its socket on the board, flick the power switch on, make sure the done and the power lights are lit up. If we do have a keyboard, make sure that the keyboard is also turned on. So then it's just a matter of letting the kernel boot and playing around with the software. So here we can kind of go over to the control page, go over to the FMCOMMS3 tab, look at the block diagram, which is exactly the same picture you saw before, where you can understand how things work, look at a picture of the board, go back to the block diagram, go over and control the actual device. So here we can actually see that the receive and transmit are set for the same frequency. So we'll quickly do that, set both things up to 2.4 gigahertz. And then we'll actually have a look at the signals. We can see what the RSSI is like, or the receive strength signal indicator. Come over, look at some things in the frequency domain. Hit the play button. So now we'll just turn on a few markers. Look at peak markers for right now. We can do this as soon as the markers show up, and then turn on some FFT averaging. When we turn on the FFT averaging, we can kind of see that distinct shape of the continuous time delta sigma. We can take advantage of the programmable 128 tap FIR inside the 9361 by loading up an LTE-20 bandpass filter. This will take advantage of the noise shaping the continuous time sigma delta converters provide and further push the noise floor down. You can see that here when the filters get enabled. Here we'll just do some quick measurements. The FFT does have averaging. When the averaging is set to 0, it is a peak hold. So if you want to kind of see if you have spurious signals popping up, you can actually quickly kind of test that with this setup. It does have quite a bit of averaging, up to 127. If you put the FFT average up to 128, it'll do a minimum hold, meaning it'll take the noise floor and push it down to the minimum it's ever seen, so that if you do have spurs, you can actually tell the spurs between random noise in your noise floor. We'll actually take the average, set it back to 8. It'll come back up. We can have auto scaling. We can turn that off. We can zoom into our area of interest, or our bandwidth, RF bandwidth, which is probably 10 megahertz right now, or 20 megahertz, and kind of see that. And then you just get your signals of interest, and don't have to worry about the extra. We can turn that off. We can come over and we can actually look at things in the time domain. For example, look at our I and Q signals in the time domain. We should see some sine waves, which we do. It's kind of hard to tell because they're flipping all over the place. There's no trigger. We can set actually a trigger up. Just turn the trigger on voltage 0, set it to 0 volts. And now when we hit the play button, our trigger is mostly stable. So what we'll do now is just add a math channel. Just come over, right-click on math, new channel. This will take any kinds of equations that you can run through a C compiler. So what we'll do is we'll do actually a power. So we'll do the I squared plus Q squared, take the square root of that. We'll go OK. and then our show's up, and then it should be basically 1 if our signals are orthogonal, which it is. Now we've seen that kind of work. We'll actually switch domains. We'll move from the time domain into the constellation. So constellation is basically an XY plot. So for a perfect CW signal or continuous waveform, we should see a circle, which we kind of see. This isn't quite a circle because the scales, the axes are a little off, but you can kind of get the idea of what it is by looking closely. If you were to have QAM or QPSK, you'd actually see that. We can actually do cross correlation of the complex signals to get like angle of attack for MIMO type things. So here we can actually kind of look at things, set the auto scale up. Here we can kind of tell the signal is not very well correlated because it's jumping all around, and it's we don't have any actually big peaks. So we'll actually flip back the time domain, and we'll actually look at these signals. We can tell that, okay, well, these signals are definitely not even close to being the same. So what are they? Well, we'll actually go back and we'll look on what the FPGA is transmitting out, and here we can see that one is a 9.2 megahertz and one is a 1 megahertz. So we'll actually switch things down to they're both exactly the same frequency to be 1 megahertz. We'll go back to the waveform, hit the play button. Now we can see things are looking good in the time domain. We can stop that, go back over to the cross correlation. Again, click the auto zoom, and now things aren't moving and it's constant, and there's peaks, and the peak is around 0, meaning that things are very well correlated. We'll just stop that for a second. Go back to the frequency domain for a sec. You can see that we can't do signals or FFTs of both channels at the same time on the same plot, but what we can do is actually open up multiple plots. If you go back to the main window and do File, New Plot, then you can actually bring up the same channel, other channels. You can have one channel, one plot doing peak detection, one channel doing, or one plot doing minimum detection on the same channel. So that your FFTs are averaging is different, the same, whatever you'd like it to be based on what kind of application or what kind of signals you're looking for. So then we're coming back over to the main FMCOMMS3 page. Looking at the RSSI again, we can see where the hardware gain is. The hardware gain is set up for in this mode, slow attack mode, but it can be changed to other things. We can look at the block diagram again. Anything in the block diagram should have a control. Anything that has a control, you should be able to find in the block diagram. So this kind of wraps things up. When you're shutting down, make sure you bring up a terminal, do sudo shutdown. Thanks a lot. If you do have any questions, make sure to come by the Engineer Zone at ez.analog.com.